Hello students, welcome to lecture 16 of your course Advanced Calculus and Special Functions. In this lecture, we will discuss the recurrence relations related to the Legendre polynomial. So before moving on to the recurrence relations of the Legendre polynomial, you must know what is the meaning of this term recurrence relation. Usually the recurrence relation, the word recurrence is formed by the two terms re plus occurrence. Means something is occurring again and again, and due to that we are obtaining a sequence of values or certain and sometimes sequence of functions. Then such a relation which gives you a sequence is called a recurrence relation. For example, in very simple terms, if we look at the sequence, suppose I am having the value a0 is 1 and a1 is suppose 2, and I give a relationship an plus 1 is equal to an plus 2 an plus 2 here. So now we can get the values, or we can get the values of the further terms from here. Suppose I want to find this value of a2, then how I can get value of a2? You just first of all you just take it in this side. 2an plus 2 is equal to an minus 1. So if you take this 2 from this place, it is here. Now if you want to find value of a2, then you have to put n equal to 0 over here, 0 over here. So when you put 0, then you get a2, but when n is 0 here, then it's a0 minus n0 here, then it gives you a1 divided by 2. What is a0? A0 is 1. What is a1? This is 2, and divided by 2. This is minus 1 by 2. That means you can get this value of a2. Well, is one term of the next term of the sequence you are obtaining from this relation. And similarly, when you find the value of a3, then what happens? You put here n equal to 1 so that you can get here a3. So when you put 1 here, you will get here a1 and here a2 divided by 2. But you have already know that this, you already know this a1 is 2, and value of a2 you have obtained over here is minus 1 by 2 and divided by, so this is in fact 2 plus 1 by 2. This is 2 and a half, that means 5 by 2 divided by 2. This gives you 5 by 4. So this way you are getting a3, and so on like that. In fact, from this relation you can get all the terms of this sequence. So such a relation is called a recurrence relation. Such a relation is called a recurrence relation. So we can also talk about the recurrence relation in case of the Legendre polynomials, because you know the Legendre polynomial of first kind is p and x, means there this is Legendre polynomial of degree n. So n is actually a number here. That is why from here we can get the sequence p1, p2, x, and so on and so forth. So exactly in the case we are talking about here for the numbers, we can also talk about the similar situation regarding the Legendre polynomial or Legendre function. So that is why we can also derive, or we can also form certain recurrence relations. So you can see here the certain recurrence relations are given over here. The first one is to show that npn, you can see this is the relation between pn. In fact, here the meaning of pn means it is the function pnx, in fact. So, and for the simplicity, this has been denoted like pn. Similarly, if you are having pn minus 1, in fact its meaning is pn minus 1 x, etc. So that is how this is the first relation which you have to show. or which you have to establish, that value of nPn will be equal to 2n minus 1 x pn minus 1 minus n minus 1 pn minus 2. So similarly, from this relation, this can also be expressed in this form or in this form. So in the examination, you may be asked to derive this relation either this way, or this way. The second relation is nPn equal to x into pn dash and minus pn minus 1 dash. So in fact here, the meaning of pn dash is dpn, because pn is a function of x by dx. This is meaning of pn dash. And similarly, the meaning of this pn minus 1 dash is d pn minus 1x, means derivative of pn minus 1x with respect to x. So that is the meaning over here. The then second relation is this. Uh, Fourth relation is here. I think third something is missing here. So this is fourth we are writing here, and this is fifth and sixth. In this way, we can derive all the relations. Fine. So the proof of first relation. What was there in the first relation? We wanted to obtain the relation in this way, that Pn is connected with Pn minus 1 and Pn minus 2, and n is greater than or equal to 2. And of course, there is the variable term x is multiplied with this Pn minus 1. So how we can obtain this? Obviously, here x is multiplied with uh, how we can obtain this one? Just replacing n with n plus 1 here, we'll get this term. Okay, then after rearranging the term, we can obtain this one. So in fact, the main clue to derive this relation is that there must be some variable multiplied with this pn minus 1. Then how we can obtain this variable? So again, as we have derived certain relationships in the earlier lecture, we consider the generating function. You know that the generating function for the Legendre polynomial is this one: 1 minus 2xz plus z square raised to power minus 1 by 2. Then this is equal to n going from 0 to infinity summation, and z raised to power n, this is nothing here, z raised to power n p n x. This is equation 1. Now you want to bring x in the multiplication with pn minus 1. So how we can do that? So just differentiating both sides of 1 with respect to z. So what do we get? In fact, differentiation of this term with respect to z gives you minus 1 by 2 and minus 3 by 2 here, minus in fact 2x plus 2z. This 2 is taken outside and this will be cancelled out, and you take minus sign outside from this bracket, then minus minus is plus, so that you can get uh, x minus z due to this factor, and this term is remaining as such here. And in right hand side, when you are differentiating with respect to z, it gives you n z raised to power n minus 1 pnx. Okay, now we want to reduce this term to pn. How we do that? We just multiply both sides with respect to with this term. So what do we get when we multiply this? It means plus 1 will be there, so minus 3 by 2 plus 1 gives you minus 1 by 2. So in fact, after multiplication with this term, the left hand side of this expression becomes like this, and in right hand side you multiply this summation with this n z raised to power n minus 1 pn. Okay, now what is this? This is in fact from equation 1 is equal to this quantity. So we are replacing this quantity with this summation. Right? When you multiply the whole summation with the first term, that means with x, and that with z, and in right hand side also we are having this type of expression, then you can see in left hand side we have multiplied the summation with x, and when multiplying with z we are getting this term, and similarly in right hand side we are doing these things. When we equate the coefficient of z raised to power n on both sides, so z raised to power z raised to power n the coefficient of this is, in this situation, x into Pn, and in right hand side you can see also when you open this, where do you get z raised to power n? You will get z raised to power n, because at the when you are having n plus 1, z raised to power n plus 1, the coefficient is Pn. But when you will have n only, so if you then the coefficient will be Pn minus 1. That is why in left hand side this is there. It is coming from this summation. The coefficient of z raised to power n in this summation, when you open this, will be Pn minus 1, and in this the z raised to power n will give you the coefficient x into Pn. That is there in left hand side. Now in right hand side, the coefficient of z raised to power n we can obtain here. Here it is minus 2xn, minus 2xn Pn. Fine. And here again the coefficient of z n, when you take z n, then definitely you have to reduce n by 1 here. It will be n minus 1 and it will be Pn minus 1. So this term comes out from this summation, and coefficient of zn in the summation will be this. And from here if we look at the coefficient of zn, then when you can see, when here the power is n minus 1, you are having Pn n, and when you raise power to n, that means you are adding 1 here. So of course you have to add 1 here, Pn plus 1, and here it will be n plus 1. So that is why this term is coming from this summation. So by equating the coefficient of z raised to power n on both sides, we get this expression. So after simplification, this n plus 1 p n plus 1 2n plus 1 x Pn minus np, right? So but what was there in the statement, we wanted to prove that npn is 2n minus 1 x Pn minus 1, means you wanted to have that coefficient this Pn minus 1 must have the coefficient x, and here 2n minus 1. Just focus on that. So x is here, but with x we wanted to have Pn minus 1. So let's replace in the whole expression n with n minus 1, so that you can have here x into Pn minus 1. When you replace n with n minus 1 here, you will get 2n minus 1. And when you replace n with n minus 1, so n minus 1 plus 1, 1 goes with 1, so n. And when you replace n minus 1 here, n minus 1 minus 1 plus 1 cancelled out, and we are getting Pn minus, again you are replacing n with n minus 1 here, so that is there, and similarly here you can get this. So this is the case we wanted to obtain here. This is this expression. Now in other form, the second one, this one was already obtained, and if you want to put it in this form, that can also be done by rearrangement of the terms here. You just keep xpn on one side and other things on other side, you will get this expression. So that is how we have established one recurrence relation. Then second relation we wanted to show. Let us see what is there in the second recurrence relation, which was given there in the statement. In the second relation, there is an involvement of the derivatives of Pn. Okay, so means we have to differentiate, of course, with respect to x. So first we are taking the relationship, this one. This is the generating function for the Legendre polynomial. Now we differentiate it with respect to z, then we get this expression. This is the same case as we have done earlier. Why we are doing this? Because in this expression also we require x in the multiplication. So that is why we have to differentiate it with respect to z, so that we get x explicitly here, and that will be in the multiplication with the expression. Fine. So again we differentiate it with respect to, first we have differentiated with respect to z, now we are differentiating with respect to x, the same expression. So differentiation of first function with respect to x gives you one here, first function derivative of second, then second plus derivative of first, like that. So in this way you get here this quantity, and in right hand side, because you are differentiating with respect to x, so here in right hand side the um, function of x is Pn in fact, so that is why you differentiate it, it gives you Pn dash, right? So in fact this expression is coming after simplification, it is not directly from here. After simplification you can get this expression, and we are having this thing. Further, when we multiply this expression both side by x minus z, so that what will happen, because you know this part x minus z into this quantity is equal to this one from equation 2. So in place of this I can write this expression, this summation term, and z is there, so z is there and the summation term in place of this whole expression. And in right hand side we are having x minus z, z raised to power n p n dash using 2. So you take z with this, so we are having n z raised to power n pn, and here in right hand side we are, if we are multiplying this summation term with this and this, we get this term. When we equate the coefficient of z raised to power n on both sides, we get the desired recurrence relation. This was the second relation we want to establish. Now the third, actually the statement of third was missing there in the first slide. So in fact third relation is we wanted to establish is this one, this one. Okay, so in fact these relations can be derived from the already approved relations. For example, here from the recurrence relation 1 we know that this, and differentiating this with respect to x we are getting this expression, or we can write in this way. Again from relation 2 we know this term. So using all these values, here you are having 2n plus 1 npn plus pn dash, npn plus pn minus 1 dash. In fact in place of this you can write x into pn dash, x into pn dash here. Yeah, in place of this it has been written over here. So after a simplification we are getting 2n plus 1 pn is equal to pn plus 1 dash here, because n plus 1 will be cancelled out on both sides. Then this is pn plus 1 dash and minus pn minus 1 dash. Now replacing n with n minus 1 we get this value, and in fact the meaning of this is derivative of p n with respect to x. Meaning of this is derivative of pn minus 2 with respect to x, and this is 2n minus 1 pn minus 1. So this was the required result. The fourth relation can be obtained using the relation 2 and 3. So relation 2 was this, and relation 3 is this. Now subtracting, just first we go back to relation 4. What was there we wanted to prove? In relation 4, actually you can see n plus 1 pn is equal to pn plus 1 dash minus x pn dash. Similarly, or this can be put in another form, pn dash minus x pn minus 1 dash and np n minus 1. Obviously you can easily see that this is directly coming from this just by replacing n with n minus 1. If you replace n with n minus 1 in this expression, you can get this one. So either prove this or prove this, that is the similar situation. So how we do that? Because here you can see xpn dash and pn plus 1 dash is there. So when xp in the second expression you can see xpn dash is there, and xpn dash has its relationship with npn. So here we require n plus 1 pn, so that means this can be utilized here. So while proving this expression, this recurrence relation here, we are writing the recurrence relation 2 as well as the recurrence relation 3 here. Now subtracting 1 from 2, we get this relation. It is direct calculation. Just using recurrence relation second and third, we can directly obtain the recurrence relation fourth here. Now fifth. For proving the fifth recurrence relation, we can utilize the relation second and fourth. Relation second and fourth. The relation second is here and relation 4 is here. Replacing n by n minus 1 in 2. So we are replacing n by n minus 1. So here it become n, it become pn minus 1. And when you are replacing n with n minus 1, it becomes pn, and this is x pn minus 1. Multiplying both sides with x, we get this thing. Subtracting, we get this expression. Similarly, we can prove this fourth relation. Actually, similarly, you can do this. Then there is the Beltrami result. This is also a recurrence relation of the same kind. It can be done in the similar manner. So, thank you. That's it about this lecture.